electric field due to a dipole. We have completed the first case when the point is on the axial line. When the point is on the equatorial line, we have to find out the field. Now, field here, because of the positive charge is acting along this direction. Field here, because of this negative charge is acting along this direction. Since the point is at equal distance from the positive charge and the negative charge, magnitude of the electric field here will be equal. So magnitude of E plus also will be same as magnitude of E minus. Both are equal since distance is equal. Now it is given by this 1 by 4 pi epsilon 0 q divided by r square plus a square. This is r and this is a. So distance of the point from the charge is r square plus a square. Now E plus is acting along this direction. E minus is acting along this direction. So then this angle is theta. So this can be resolved into two components. Cos theta component where it is making theta and perpendicular to that sin theta component. Similarly, E minus vector also can be resolved into two components. Cos theta component and sin theta component. Since E plus sin theta and E minus sin theta are equal, it will get cancelled. So total electric field will be given by this expression minus magnitude of E plus cos theta p cap minus magnitude of E minus cos theta p cap. Because it is acting along the negative x-axis, or dipole moment will be acting from negative charge to positive charge. Field is acting in the opposite direction, that is why minus p cap. Now magnitude of E plus will be same as magnitude of E minus. So it is given by this expression 1 by 4 pi epsilon 0 q divided by r square plus a square. The distance between the charge and the point is r square plus a square. This is r and this is a. Using the Pythagoras theorem, you can get this distance. So its square is r square plus a square. Now instead of this, we can substitute this expression. Similarly, for this also we can substitute this expression because these both are equal. Now after that you will get like this, because it will be 2 times of this, because this and this equal, so it will be 2 times of this. After that step you can get like this, because cos theta is adjacent side by hypotenuse. For this, from this angle, cos theta is adjacent side divided by hypotenuse. So so substitute for this cos theta. Cos theta is a divided by square root of r square plus a square. So you can get like this. After that step, you can get like this. The reason 2qa p cap is p vector. Then suppose r is very much larger than a. So this a can be neglected. So this 2 will get cancelled. So you will get r cube. So this is the expression for the total intensity when r is very much greater than a. When the point is on the axial line, field will be double of this. There will be an expression of 2 when distance is very much larger than a. Field here, when the point is on the axial line, field will be double of this, but it will be acting in the direction of the dipole moment. But when the point is on the equatorial line, it will be acting opposite to the direction of the dipole moment. It will be acting along this direction. That is why there is a negative sign. Important inferences. Suppose there is a point charge at a point A. Electric field at a point P, which is at a distance r, is given by this relation. So electric field is inversely proportional to the square of the distance of the point from the charge. Now, electric field due to a dipole. So here two equal and opposite charges are there separated by a small distance. electric field at a point on the axial line is given by this relation. When the point is at a large distance, R is very much greater than A. So this is the expression for intensity of the electric field. This is valid only when the point is very far away from the electric dipole. From this is clear, electric field is inversely proportional to the cube of the distance. Here it is square of the distance, here it is cube of the distance. Similarly, when the point is on the equatorial line, when it is given by this relation, when R is very much greater than A. Here also intensity is inversely proportional to the cube of the distance. From these two expressions, it is clear electric field at a point on the axial line is double than the field at a point on the equatorial line. So here field is inversely proportional to the cube of the distance when R is very much greater. So these two expressions are valid only when R is very much greater than A. So here it is inversely proportional to the square of the distance, here it is proportional to the cube of the distance. So the reason is when for a large distance this charge appears to neutralize negative charge, positive charge. When R is very much greater than A, this charge appears to neutralize each other. That's the reason here it is square and here it is cube. Now this is valid only when it is R is very much greater than A. But one special case is there. Suppose 2A approaches 0, it is becoming lesser. 2A approaches 0 and Q approaches infinity. But P is finite. In such cases, these two expressions are applicable for any distance.